We'll be talking about stabilizers, orbits, and group actions in general. Firstly, what is a group action? Well, let's say I have the elements of the symmetric group S3 right here. So let's write all 6 of them out. First, we have the identity 1, 2, 3 maps to 1, 2, 3. Then we have the second element 1, 2, 3 maps to 1, 2, 1, 3, which is just one transposition. Then we have 1, 2, 3 maps to 3, 2, 1, which it happens after a transposition and then a cycle. Then we have 1, 2, 3, 2, 3, 1, which is just one cycle. Then we have 1, 2, 3, 1, 3, 2, which happens after we do a cycle and then we transpose. And then finally we have 1, 2, 3, 3, 3, 1, 2, which is what happens when we cycle twice. So you can see there are exactly 6 3 factorial elements, since there are 3 factorial permutations. So now, applying can mean many different things. But in this context, let's say we have a set A of cardinality 3. Well, no, not like that. Sorry. Let's say we have a set A. And this set is a set of all the different possible permutations of 3 elements. So A1, A2, A3. Then A2, A3, A1. Just think, what if S3 was turned into a set? Then, applying S3 to A means we take some element S and then multiply some ordered pair inside A to get our answer. And it can be left multiplication, right multiplication, or anything else you can think of. For example, if they are ordered pairs of matrices multiplied by another matrix, it could be something like this. So, next, what is a stabilizer? Well, the thing is, dihedral groups are groups too. So let's say we have a square like this. All we're going to do is we're going to apply the dihedral group to this square right over here. This is a group action. Put the 4 vertices in a formation like this. Now I'm going to label them 1, 2, 3, 4. If I rotate them this way, clockwise, then 2 goes to 2 goes to 3 spot, 3 goes to 4 spot, 4 goes to 1 spot, and 1 goes to 2 spot. Kind of like a cycle back in symmetric group 3, right? So, reflecting swaps 2 back with 1 and 3 back with 4. So what we can do is we can cycle it twice so that 2 takes 1 spot and then reflect it so that 1 takes back its original spot by trading with 2. So I'm going to illustrate it this way. If I rotate it this direction, clockwise, now 4 is here, 1 is here, 3 is here, and 2 is here, and 3 is here. And then, if I now reflect it, 1 is here, 2 is here, 1 is here, 2 is here, 3 is here. Okay, no, I'm not going to do it that way. Okay, so let's say I rotate it like this. So we get 4, 1, 2, 3. And then we rotate it, no, reflect it about this axis. Wait, no, sorry. And then we reflect it about this axis. And what do we get? We get 1, 4, 2, 3. And you'll be able to tell that these opposite corners have had their locations preserved. So the stabilizer of vertex 1 and vertex 3 the stabilizer of these two is the element of our group D4 that we denote as a rotation x squared followed by a reflection y. And you can actually do almost the same exact thing with these other two vertices right here. Wait, no, sorry. This would be yx. These other two vertices right here. You can test it out yourself. They are conserved by yx cubed, which by the rules of D4 turns out to be equivalent to xy. Alright, so that's what a stabilizer is. Finally, what's a group orbit? Well, what is an orbit in astronomy? Well, if we have the sun here and the Earth in this orbit right over here, you can tell spring is when the, that's definitely not to scale. Spring is when the Earth is right here. Summer is when the Earth is here. Fall is when the Earth is here. Winter is when the Earth is here. So, you can tell that the Earth's got one of 4 possible states, and it's going to keep cycling through them. And I know this is not an accurate analogy to all of you astronomers, but to the people who don't know astronomy, like me, this is perfectly fine. Don't tell Refat I'm making this. So, a mathematical orbit practically has the same definition. Like, let's say that D4 from earlier, we have this element, D, right here. An orbit under D is a little chunk of the set that cycles inside itself. So, for example, let's take the orbit of element Y right here. Originally, our vertices look like this. Reflecting them, the vertices look like this. And then they go back to their original state if we reflect them once again. So 1 exchanges positions with 2, and then 2 will go back to 1, and so on and so forth. So vertex 1 and vertex 2 become their own orbit. And similarly, vertex 3 and vertex 4 will keep swapping positions with one another, making themselves their own orbit. So that means that under this element of our group, our set is decomposed into 2 orbits, each of order 2, since they have 2 elements within them. So, if this is what an orbit is and what a stabilizer is. Now, let's try and attack a problem that uses all of these concepts. Let's say we have a cube like this. Everyone knows what a cube is. Now, let G be the total number of let G be all of the rotational symmetries of the cube, like the dihedral group, but in 3 dimensions. Now, you'll probably figure out that since there are 4 rotational symmetries of the square, and there were 6 faces, and we're not considering reflections at all, there were 24 rotational symmetries. So, there were 24 elements in this group, right over here. So, we decompose this into a bunch of subgroups. And And if we pick a specific vertex v, gv will preserve that vertex. Not all the vertices, it's impossible to do that. It's not the identity, or what we'll come to call a conservative rotation. Just a single one of these vertices. Wait, no, cut the conservative rotation. Well, no, it can't preserve all the vertices. That's only possible with the identity. It only preserves this one vertex right over here. So GE does the exact same, preserves one edge E. So we can go into this face and out of this face, kind of like that. We can go in through this face and out through this face. And we could go in through this face and out through this face. So there were 3 different axes around which we can do rotations and keep this symmetrical. So I'm going to call this first axis the X, the second axis the Y, and this third axis the Z. Now I'm going to call any rotation around the X a rotation of 90 degrees, rho X, a rotation of 90 degrees around the Y, rho Y, and a rotation of 90 degrees around the Z, rho Z. And of course, these all have the property that if you repeat them 4 times, it'll just give you back the identity. So let's figure out what happens when we transform things like this. So let's say I have a specific vertex, one that's really special and that I really want to preserve. Like let's say this one right over here. How can I rotate it? Because obviously the identity preserves it. But what other rotation can I do to preserve it? Well, let's think about this right over here. We could rotate it around the x-axis like that so that it exchanges positions with this vertex right over here. And then what we can do is we can rotate around the y like that so that it will return back to its original place. So what we just did was a rotation in the x by 1, followed by a rotation in the y by 3. And you'll find no matter what, PA cubed, PB, A and B being any of the axes, or PA, PB cubed, these are all conservative of some specific vertex, V. So, this is just one of the possible ways to conserve it. Now, you can actually figure this out because this vertex is part of 3 different faces. That means you can basically replicate this exact scheme 3 different times, meaning there are 3, including the identity, 4 different elements in our collection of preservatives. So there are 4 elements in this group that preserves a specific vertex V. So now let's talk about E, the edge preserver. It's basically the same exact thing. Like for example, let's take this edge right over here. You can rotate it around the z-axis so that it travels here, and then you can rotate it around the y-axis so that it goes back to its original place. So all you get is, well, pz squared, py squared. So anything of PA squared, PB squared will conserve some edge. And of course, since one edge is part of 2 different faces, you can find 2 different ways to do this. Meaning it's 2 plus the identity is 3 different elements in E, GE. Now, about conserving faces, you can only do that through what I call a conservative rotation. So, for example, if you want to conserve this face right here, the only thing you can do is rotate around the y-axis right over here, because otherwise this face is going to be displaced. Well, actually, no, that's not the only thing you can do. So PYN can conserve this, but also imagine rotating it by 180 degrees over to the opposite face right over here, and then rotating it around the x-axis to go back to its original state. So that's pz squared px squared. Px squared pz squared. So, sorry. So how many elements are in this, actually? Well, you'll realize that these two aren't totally separate in different universes. They can actually be composed. So there are three different ways to rotate it this way, since we're excluding the identity. But if we include the identity, that becomes 4. And then composing it with how many there are to do things this way, pz squared px squared or px squared pz squared, that becomes, well, 2, which becomes 8 in total. So that means that we have 3 different elements here, 4 different elements here, and 8 different elements here. So if you want the original question, you can travel into Michael Arden's Algebra 2nd Edition and go to Chapter 6, Question 9.2. So this has been Group Action, Stabilizers, and Orbits.